So let's have one quick definition first, which we're gonna use this definition in this course, and that is allowable versus design value. So allowable, which we're gonna focus first in this course, are basically your let's say you're measuring a strength. It's the value that you want to report for strength of the material. What value you report? In that reporting, as you will see in a second, we're going to include the statistical distribution of the material. So we're going to reduce, you're not going to report the average, the mean response from like a bunch of tests you have done. You have to be on the safe side. So you're going to report lower values. So you look at the statistical distribution of properties, and you're going to report a specific lower bound value. We call those allowables. So this allowable basically considers the fact that the material has variability. So when you're making a structure, it might not be that the material is at its highest strength or middle strength. In worst case scenario, you're building the structure with the variability where the material has its lowest properties. So that's allowable. Then when you want to design a structure, you're not using those values directly, because there are many factors that might come in to reduce those properties. For example, there might be environmental conditions, hot temperature or humidity, that can reduce these design values. There might be some specific areas where you have bonding, which we're going to cover, that reduces these values. So we have some knockdown factors that reduces those allowables, and then we will get what we call design values. So design values are then used to design a structure and build a structure. So again, allowable considers the statistical variation of material properties. Design values, on top of that, apply some knockdown factors to reduce that value to consider things like high humidity or high temperature. Okay, so let's first talk about allowable. And I'm gonna jump between my slides and my whiteboard on my laptop. So let's actually do this on the whiteboard. It might be easier. Okay. So let's say we are doing a test, and just let's keep it simple. We are doing a tensile test. But we are repeating this many, many times. The same material, the same condition, we just keep testing it. Once this is done, I plot a distribution. So on the x-axis, for example, from all of these, I'll calculate an average. Let's call it mu. So there's an average. 600,000, whatever it is. Let's say 100 megapascal was the strength that we measured on average from all of these n samples. And then let's say this was a normal distribution, which might not be. It could be that you do this test and you see that it doesn't fit normal distribution. For our purpose, let's say it was normal distribution. So this is probability, and this is, let's say, that value. And you get a distribution like a bell-shaped distribution like this. Higher values of strengths is very, very rare. Lower value of strengths, very rare. There is a mean response, which is mostly the material strength happens around that. But you get lower, sometimes you get lower values, sometimes you get higher values. Let's say this distribution also has a standard deviation, which is called sigma. If you are familiar with this normal distribution, you can calculate at what percentage of the materials are, let's say, lower than 1%, what condition, how many materials are less than 1% strength, how many are less than 10%. So it's like if you divide it into buckets, what strength shows that the material, the 10% of the materials are here, 90% of the materials are there. What is this value? Or what value represent the first 5 percentile or 1 percentile? The first 10 percentile is approximately mu minus, what was it, 1.6 something, 1.65 times sigma. So if you calculate this value, it gives you a lower value here, which is the 10th percentile. So this means that for approximately 10% of the tests you have done, the strength was lower than this value, which is a value smaller than your average. The first percentile, again, let me look it up because can't remember what was the first percentile. What's the first percentile? Doesn't anyone know? 2.5. Yeah, it's 2. So the first percentile is mu minus 2.576 sigma. So if you calculate this value, it will basically tells you that 1% of all the tests are smaller than this value. So mu means that 50% of the tests are smaller than it. Mu minus 1.65 sigma, that means that 10% of the tests are smaller than this value. Mu minus 2.576 times sigma, that means that 1% of the tests are smaller than this value. Is this clear so far? That's the first percentile, that's the 10th percentile, and that's the average or mean. Okay, so if someone asks you to report property of this material, you might say that this is a normal distribution with an average of mu and a standard deviation of sigma. But typically in design, we rely on these lower values, not the average. I have to describe to you the exact language, but this typically this 10th percentile, we call it B basis allowable. How do I write basis? Basis. And this is A basis allowables. So A basis and B basis. So when someone says, oh, what's the A basis of the material? That means that go and do a lot of tests, plot them, the distribution, look at the lowest 1% strengths, report that to me. If someone says, what's the B basis allowable? The same thing, you're looking at the first 10 percentile and report that as a value. This sounds simple, but there's a catch here. How many tests do I have to do before I get a good distribution? And that's a point of debate, as you will see in a second. To make it clear, FAA says you have to conduct enough N such that you are 95% confidence in the values you are reporting. So this 95% is not distribution, it's your confidence level. You say, oh, I have done 5 tests and I'm sure that the first percentile is, I don't know, 5 megapascal. How can you be sure if you have only done 5 tests? It's not enough because 5 tests doesn't show you the distribution. You need to have done more tests to get the proper distribution, right? So far, is that clear? Let me go back to my slides. I'm going to come back here again. Okay, so basically, again, the way we do a lot of tests. We plot the distribution of properties, and the average is mu, and mu plus minus multiplier of sigma shows you the percentile of distribution. This distribution, why do we have distribution, first of all? It's because the initial material has variability, and it's because our fabrication process has variability. So if you do this enough, you start to see a distribution. And again, it doesn't need to be normal. Sometimes it's actually not normal distribution. It's like Weibull distribution or log normal distribution. And this is the way we define A bases and B bases allowables. And again, allowables are the properties that consider the fact that there's a statistics attached to material properties. A 95% lower confidence bound on the first percentile is called A basis. That means that look at your first percentile, it's a very low value. Report that, but you have to be 95% confident in that value. B basis is a 95% lower confidence bound on the 10th percentile. Again, it says, look at your distribution, report to me the first 10 percentiles. And when you're reporting that, you must be 95% confidence in that reporting. Right? So far, it's clear, but there is a hidden catch here. The hidden catch is this forces you to do a lot of tests, and tests are expensive, and no one wants to do a lot of tests. So there is some free room here that you can decide to do a smaller amount of tests, but then you have to pay the price. And one of the discussion topics today is about that the price that you have to pay. How many tests are enough? And then what's the cost associated with your decision? So I'm going to explain that slowly as we go through this. But first, before I do that, let me actually define this. Going back to my whiteboard. So the proper definition of A and B bases are, you get your, let's see what is the proper, how do I refer to mean and standard deviation? So X bar is the average, let's say, minus a factor times standard deviation. That's the proper definition of A and B bases. For A bases, you say Ka. For B bases, you say Kb. These are just numbers, K and Kb. But let's properly define that. So that's the A basis, and that's the B basis. You find your average, you find your standard deviation, then there's a factor, and we call this a tolerance factor. If you do unlimited number of tests and you have an extremely good confidence in the distribution, this Ka value from what I said is equal to something, where was it right there, 1.65, no, sorry, 2.57, almost 2.6. And this Kb is approximately is equal to 1.56, 1.6. If you do enough tests, unlimited tests. But what if you don't do unlimited tests? You can never do unlimited tests. You have to set the bound somewhere. So you have to select a number of tests that works for your budget. If you do just a few tests, for example, 5 or 10, in order to get confidence in the value you're reporting, FAA asks you to increase these values. So let's see what's the effect of that. FAA says if you're not sure about your distribution, you have to increase that K factor. That reduces your allowables, A and B. So here's the connection. If N is low, K goes up. Therefore, A and B goes down. Therefore, the strength you're reporting is going to be very small. Therefore, your design is going to be very heavy because you have to increase the thickness of the parts such that with that lower strength, they can still carry the load in your design. So it's there is a weight penalty that applies. And here where the cost comes in. When you reduce the number of tests, the amount of money you're spending goes down. But then your design becomes heavy, your manufacturing becomes heavy, the cost of manufacturing goes up. And that's the choice that you have to make as an aircraft fabricator. So as an engineer, you have to make the decision. You have to suggest that if you are doing this design, what should be the proper number of tests such that you're not doing a lot of tests, so the cost of testing is low, but your design also is not getting too heavy. Did you guys understand this? Was this clear, this trade-off between number of tests and the design?
Yes, but you're saying that A and B are the number of tests for that percentile?
Yes, so you're just doing, let's say, 5 tests, and you're not too sure about the statistics. So FAA basically penalized you for that. They ask you to lower your reported values such that it still gives you that 95% confidence. That's why, I mean, statistically, we can explain why we have to increase K and B, KA and KB. But when you increase them, the outcome is that the A and B bases are dropping artificially to make sure that you can satisfy that 95% confidence. If you do more tests, 10 tests, then K and B, KA and B, they go a bit lower. More tests, they go lower. All the way to, if you do unlimited number of tests, they reach 2.5 and 2.6 and 1.6.
Also, one more question, Professor.
Yes.
Does the FAA have any standards for like S-basis testing?
S-basis?
Yes.
I forgot, what was the S-basis? I can't remember. What?
I think it was more of a custom or restrictive.
Okay. I don't know, honestly. I can look it up. On top of my head, I can't remember.
Okay, thank you.
Other questions? This is quite important for our course. So make sure that you truly understand this this example. Let me go back to my slides, and I come back. I'm going to do a bit of calculation so you see the effect of that. Where is my slides? Okay, so this is the proper definition of A and B basis. Mean minus tolerance factor times the standard deviation. And FAA tells you what are these values, Ka and Kb. So there are plots where the x-axis is your sample size, how many tests you have to do or you have done, and what's the value of K that you have to look up for Ka and Kb. And this table on the right also shows that. For example, if you have 3 samples only, the values of K and Kb are really large. And then as you increase that, it drops. Typically, it's suggested to do around 30 tests or 40 tests for A bases and around like 18 tests or 15 tests for B bases. And kind of see that it's kind of like it stabilizes. If you increase the number of tests, the strengths, the allowable that you can use in your design doesn't change much. It's kind of like becomes constant. But at the beginning, for the first 10, 15 tests, it has a significant effect. So if you do only 3 tests, your design value will be much lower. So let's do an example where you can see that effect. Okay, here's the example, which is also in your slides. Let's say that you have done a lot of tests. Unlimited number of tests have been done. And out of this, you have measured that the average of tensile tests that you have measured for this unlimited number of tests is 100 megapascal. Oh, Owen, you have a question? Owen, do you have a question? Go ahead and ask if you have a question. I don't know why I can't hear you. Oh, we can type if you type your question. While Owen is typing, let me write down. Let's say again, you have done a lot of tests. Out of that, a lot of tests, you have measured that the average strength is 100 megapascal, and you have measured that the standard deviation is 8 megapascal. What is B basis for this test? So according to what I just described, B basis is X bar minus a factor KB multiplied by standard deviation. And for unlimited number of tests, KB is 1.645. So it will be 100 minus 1.645 multiplied by 8. And this will be 86.8 megapascal. This is the value that you can use in your design. You report back this value for unlimited number of tests. Oh, the question. So let me read your question, Owen. Is the standard K basis only for the lowest? Using the same scale as a move high. Okay. Yeah, so we're going to talk about the higher up level, I think 2 weeks from now. As you can see, as we go higher up in the level, there are other knockdown factors that gets applied on these base values. You're going to see some of the knockdown for the coupon level, but as we go higher up, there will be other factors that are going to get added to these values. Okay. So the question that Owen asked was that is this only for the coupon level, or it applies, let's say, to a much larger structure? Okay, so that's the first thing. But let's say that you haven't done unlimited number of tests, which you probably are not going to do unlimited number of tests. Let's say you have only done 30 tests. By 30, I mean you have actually done 30 repeats of the tests, which is still expensive, but let's see, it's much less expensive than unlimited number of tests, right? So let's see what's the B value for this case. Let's say when you did 30 tests, your measurements are going to be slightly different than the measurement you had for unlimited number of tests. Let's say in this case, you measured an average of 99.9. It's very close to 100, but a slight difference because you have only done 30 tests. And let's say the standard deviation you measured was 7.9. So again, it's slightly different than the values that you get from unlimited number of tests. So you use the same equation to calculate B basis. 99.9, now what you have measured, minus, this time, based on the table that FAA has, for 30 tests, you have to use a K value equal to 1.776. So you increase this value because your number of tests are not unlimited. Multiplied by 7.9, and this gives you a value equal 85.7 megapascal. So this will be the value that you have to use in your design. This is a lower value than what you had before, but it's extremely tiny, the difference between them. But in turns, what did you save? You went from unlimited number of tests to only 30 tests. If every test is like $10,000, imagine how much money now you're saving, but going to this smaller batch of tests that you have to do. So it's a big saving. So as an engineer, you have to suggest to the company that you're working for that this stop the number of tests after 30. You're not gaining anything by just repeating these tests. Okay, but now let's go to the other extreme. Let's say you're not doing enough tests. This time, let's say that you have done only 3 tests. And it's definitely not representative of the distribution of the properties. But let's say in this case, you were still very lucky and you measured an average of 99.9. Very close to the value that you had before. You got lucky this time. And the standard deviation, though, is a bit different because you only have 3 tests and they were very close together, let's say. So you got a lower standard deviation, let's say 6.5. Again, these are different from the actual distribution because you only have three sample sizes. So it's not represents the actual reality. These are all the approximation that you have. If you want to measure the B bases in this time, so B would be equal to average minus KB times S, again, 99.9 minus, for 3 samples, for a sample size of 3 tests, FAA asked you to use a K value equal to 6.155. You multiply that by standard deviation that you measured, and this still gives you a value equal to 59.9 megapascal. So see what happens now. You went from 30 tests to 3 tests. The cost of testing has dropped by a factor of 10. You have saved that much money for the company during the design phase. But as a result, you have to design the entire aircraft with an extremely smaller value compared to previous case, which means that your design becomes bulkier, it becomes heavier, it becomes extremely inefficient. So it's not a good design. You are wasting a lot of money now in the design. And the proper number of tests is somewhere in between. Typically, it's recommended to do at least 18 tests for B bases. Then it's like a best of both worlds. You are partially saving on the test and you're partially saving on the design. Any questions on this example? Okay. Let me go back to where are my slides? Oh. Okay. So what we just described now is just the base level. Then there are many things that gets applied in real scenario that reduces the performance of the material, like environmental changes, high temperature, high moisture, geometry. Maybe there is a specific geometry which the material actually performs lower, which you're going to see some examples. The other one is fasteners, which we're going to talk about that. First, I'm going to talk about environment and then bonding in the rest of the lectures. But first, going back to the question that Owen also asked, when we are doing design and certification, as remember, there was a concept we call building block pyramid. At the base of the pyramids are many types of coupons, as shown here, like tensile in different directions and like in notched samples. This is the area that you have to do a lot of tests and establish this allowables and design values. You might do this at the element level as well, but you do a smaller number of tests. And we're going to cover this 2 weeks from now. But for now, let's just focus on this coupon level test that we have to do. And let me walk you through an actual scenario. This was a test program which was done. You can kind of see the number of tests and how they came up with the properties. So the first thing you want to do is that you want to explore your layup and your raw material. That's part of your design. So typically you communicate it with something like this. It's a test matrix for layup sequence and material. You're gonna, for this is again, is taken from an actual example that has been done and has been published by FAA. This example, they wanted to explore 2 types of materials. And one of them, which is like this blue triangles, are unidirectional fibers. So these are like fibers in the material aligned and parallel. This is one type of material. The other type of material, which is this hollow circle, red hollow circle, are fabric, which means that the fibers are like they go up and down and they create a woven structure. So it's a different style of material. But you don't know at the beginning which one is better for your design. So you're going to evaluate both. Then this triangle here shows you the entire design spectrum in terms of layup. The y-axis is the percentage of the fibers in the 0-degree direction. The x-axis are the percentage of the material in the plus minus 45-degree direction. The remaining is the percentage of the material in 90-degree direction. So, for example, if I take this hollow circle here, it says that 40% of the layers have a direction of 0 degree, 20% of the layers have the direction of plus minus 45. The remaining 40% have the direction of 90 degree. This one here, the green square, 100% 0 degree. So this is what we call a lamina. This one here is 100% 45 degree. And this one here is 100% 90 degrees. So these are like base level properties. These in the middle are laminates. You can see in this design, you're going to evaluate a bunch of laminas. You're going to evaluate different material systems. And for different material system, you're going to try different layups. 50%, 40%, 10%. And again, these percentages are the direction of the fibers. Clear so far? Okay. So you're not sure at this step what material you want to use, what layup you want to use. So they're all basically part of your investigation. In order to get the statistical distribution, you're going to follow this chart. For every combination that I just described here, which is the layup and material, you're going to manufacture 3 times. You're going to use an autoclave 3 times to manufacture batches. That brings in the batch variability. So maybe the engineers that are making it are different. Maybe you put it in different parts of the autoclave each time. That brings part of the statistics. In every autoclave run, you're going to make 2 panels. So it shows you the panel-to-panel variability. From every panel, you're going to cut 3 specimens. So overall, you have manufactured 6 panels. 3 specimens from each, that's 18 specimens total. And that 18 specimens total would be enough for you to say, what's the B basis value for this given material and layup? But there's more to this. And this table basically shows the entire test spectrum they did. How they arrived at this is a different question. They probably had a down selection process. But they said that we're going to do tensile tests, unidirectional tape only. So we are not going to do the woven one for tension, for whatever reason they had. We're going to try 3 layups, 50% plus minus 45, 40% 0, and then 10% 90, the other layup, the other layup. So 3 layups are considered. For every layup, we're going to consider a case when there is no hole in the middle of the sample versus you have a notch in the middle of the sample. And you're going to fill the hole with a putty to kind of sort of like a, or with like a bolt to show the effect of having a bolt in the hole. For every layup, for every test specimen, you're going to make 3 batches. Then you have 3 conditions that you're going to test the material. Ideal is cold temperature dry condition, which means that you're gonna dry the sample and conditioning it at -65 F for ASTM specifies that. I don't know how many hours, or maybe 2 days or 3 days. Or room temperature tests, room temperature dry. You're gonna dry it in an oven for a bit, and then you're gonna test it at room condition. Elevated temperature wet. You're going to take the sample to 180 F at the relative humidity of 85% conditions and test it. So the box says how many tests you want to do. This one says make 3 batches. Every batches make 2 panels. From every panel, cut 3 specimens. So that's the 18 samples. But you want to do it at cold temperature, room temperature, elevated temperature. That's 54 samples. Overall, you're going to test 260 samples for all the layups, test geometries, variabilities of batches, variability of layers, variability of the layup of the panels, and variability of environments. Then you're gonna do laminate compression tests. This time you're gonna do it on both tape material and fabric material. We're gonna test both material, and it tells you the layup, the specimen times, number of batches, again, all the conditions, and how many tests you have to do. And you have to repeat it twice, one for the tape material, one for the fabric material. So 216 tests in tension, 180 tests in compression with tape, 180 tests in compression with fabric. And from this, you're gonna get your B-basis allowables. It's a lot of tests. We're talking about 1,000 tests. And again, think about the fact that every test is a few $100s. It just adds up the value. Any questions so far? We're good? Okay. I'm going to move on to another important topic. And the consideration is quite often you have two structures coming together. What are the ways to connect them? And we're going to talk about two specific ways. There's a question in the chat. Okay, who is that question? One asking question. For the cost of the test, what does that incorporate? Does it include the cost of paying the engineers? Okay, so I was doing costing in a research center we were doing in the past. If the customer provides the panels, if the customer actually fabricates the panels, then the cost of cutting the panels, for the tensile test, you have to tab the specimens. So tabbing the specimens, conditioning the specimens, testing the specimens, and reporting it. Like for the tensile test, I was charging $200 per specimen. If we had to make, and I did a comparison with other testing labs, we were more or less around the same ballpark. It was varying between different labs, $150 to like, I don't know, $300. If you bring in the costs of fabrication of the part, that adds to this cost. Right, but the costing that I was doing, it was the engineer's time, it was the cost of the depreciation of the equipment. You have to consider that because you have to replace like the testing frame after a while. And there's a cost of technician to do the test, cost of an engineer to do analysis, to do data reduction, report the value. Good. Okay, so I remember I did one of these tests, for example, for Honda a couple of years ago, and the overall projects, I can't remember how many tests we did, maybe a few hundred tests, but it was around $100,000, and it was like around 6 months of testing. So the price can go up quite fast, quite significantly. Okay, any other questions? Good. Let's talk about this really, really important topic. How do you connect two parts? You can bond them, and you can use fasteners. Which one is better? In terms of which one is easier and which one is lighter, and which one is more aerodynamics, which one do you think is, first of all, fasteners versus adhesive bonding? Which one is overall better? Who has an idea? Kai says bonding is better. Who else? I hear opposing opinions. It's not surprising. Yes, it might depend on the application and the goal. Yes. So overall, you would like to do bonding because it's cheaper, probably. You don't need to drill holes. You don't need to add extremely costly fasteners. I was shocked and surprised to see the cost on these fasteners. These are not normal fasteners that you have to put in. So it adds to the cost, it adds to the weights. But then there are situations that you're going to see that the bonding is not enough. Bonding has lots of issues that we haven't been able to resolve. So if you're not absolutely sure, we typically don't put all our eggs in one basket, which is bonding. So I'm going to give you an example. Unhappy, Kai?
I thought bonding would be the perfect method without any drawbacks.
No, there are some unfortunate drawbacks. That's what we're going to cover. And I think, if I'm not mistaken, one of the discussion topics today is I'm asking you to kind of choose or compare these two. So let's go through some examples. Let's see why bonding might not be good. First of all, let's start with adhesive bonding. I'm going to switch to fasteners. Adhesive bonding, it's designed to transfer the load from one part to another part through shear. So it's designed for shear. So let's keep that in mind. But you can do this through quite a few different approaches. So you've seen some examples on the right. For example, you can take both parts and tapers them, and then kind of like join them like this scarf bonding you can see at the bottom. Quite a popular approach. You can do what we call a step cut, or you can do just a simple like lap. So it's just bonded together. There is no difference. So sometimes there's double overlap or single over. So there's different ways you can do this. I'll show you examples how this might change, or maybe it's not for this. Maybe it's for fasteners. Anyway, we'll get to an example in a second. But in addition to this, there is also different ways of connecting different types of materials. You can get what we call, let's say, two uncured composites, put them together, cure them with adhesive between them, or maybe not with adhesive between them. Let's say without any adhesive between them. So the adhesive is actually the uncured resin inside each part. It creates chemical bonds between the two uncured materials during manufacturing. This we call co-curing. You might have a case when there is an uncured part and cured part, or maybe a metallic part, so it doesn't need to be cured, and you put adhesive between them, and then you take them through curing process. We call this co-bonding. The process of making, if you remember the skin of, let's say, the wing or fuselage, where you put the stringers on top of that, is through this process, co-bonding. It might be something which is called secondary bonding, where you have already cured two parts, you just put an adhesive between them, and then you bond them together. So co-curing, co-bonding, and secondary bonding, depending on the condition that you have, you can choose between them. What are the problems? What are the defects that you might get in an adhesive? You might get void in the adhesive. Typically, the void happens if during the adhesive process, you don't have good fit up, which results in lack of consolidation. So you put a bit of pressure on adhesive, and then you apply heat and you cure it. If the pressure is not uniformly distributed, or you have a bit of gap, not enough adhesive in some areas, you will get voids, right? So that's one typical problem. Or you might have voids because there was too much moisture inside the adhesive. During manufacturing process, temperature goes up, moisture comes out of the adhesive, and then creates bubbles. So you get void because it's, let's say, it was stored in a humid condition. There might be some contamination, so you see foreign body or foreign objects or FOD. You might have some cracks because there were residual stresses. I've got to describe what are the proper procedures you can do for get rid of some of these things. I'm going to talk about kissing bond in a second, but let me define it. Kissing bond is, let's say when you were putting the two layers together, there was a bit of oil or dirt on the surface of one of them. And it's a thin layer. And you put the adhesive, you take it through the process. That section doesn't bond. Why do we call it kissing bond? Because it looks perfect, but when you apply a bit of load, it opens up because it didn't properly close. So these are typical defects. Most of them you can get rid of easily. You apply proper pressure, this doesn't happen. Delamination, we're going to talk about it. We're going to talk about it properly here. You can do a proper design to get rid of delamination. I'll show you an example. Porosity, because of moisture, you can dry the sample, your adhesive, before you take them through the manufacturing process. Cracks, you can modify your manufacturing process. Kissing bond, you can clean the surface properly, make sure there is no dirt on the surface. You can get rid of all of them. But out of all of these, the most dangerous one is kissing bonds. Why do you think kissing bond is the most dangerous one?
Is it harder to detect via inspection?
It's not just harder, it's impossible to detect via inspection. All the other ones, you can have a specialized, let's say, ultrasound technique that they interact with the gaps or cavity that you have, and it will show you where it is. Kissing bond is the only one that at the moment we have no non-destructive inspection methods to find kissing bonds. The only way to get rid of kissing bond is not to have it at the first place. If you make sure your manufacturing process is very robust and there is you follow the exact procedure every time to make sure there is no contamination on the surface, you will not get kissing bonds. But then again, this draws the question that how do you sure that your manufacturing process was perfect? Maybe this was a subcontract. Maybe it was not your own manufacturing process. How do you trust the supplier to follow the manufacturing process? Or mistakes might happen at the end of the day. That's why in some critical cases where the failure might lead to the failure of entire structure, you're hesitant to use bonding because there is no backup plan for it. You cannot detect the defect. Okay, failure might happen through different mechanisms at the bonded joints. In some of them, you are failing the adhesive itself, like this one here, we call cohesion failure. So adhesive fails. In some of them, it might get separated from one of the substrates, adhesion failure. In some of them, one of the adherent and one of the substrate might fail itself, and you might see a mixed mode. The most desirable one for us, which one do you think is the most desirable one?
Cohesion failure?
Cohesion failure is the most desirable because the adhesive didn't fail, basically. So if it happens that the bond gets separated from the substrate, that means that that's the kissing bond, let's say, similar to kissing bond. This is adhesion failure. If the adhesive itself failed, it means that the adhesive was not strong enough. Its design was not correct. So you have to modify that. So that's the idea, that you look at the failure mode and try to modify your design. Thank you, Seth. Yeah. Other problems with adhesive bonding. It's only designed to carry shear. So the moment you apply tensile load, peel stress, or other types of like bending loads on it, it is not designed to carry those types of loads. So if you want to go with the bonded joints, you have to try to eliminate the chance of the bonded joints going through this type of loads. But sometimes it's not that easy to prevent that. For example, you might have mismatch of the stiffness on both sides. That results in some of these load transfers, not all through pure shear anymore. You get some sort of like bending through the joints. It's quite common to get what we call peel stress close to the edges of substrates. So what will happen that you will develop the out of plane opening stresses, and that kind of like peels the first ply on the other side, create delamination, which causes to failure. And it happens because as you get close to the edge, free edge, these new stresses, they get developed at the free edge. It comes from the equilibrium. We don't need to go through the details of that, but you get those that we call peel stress close to free edges. One way of removing that is to taper toward the end, and that's quite common. So when you taper it, you slowly get rid of that peel stresses, and it goes to zero. So the load remains in shear mode. So it reduces peel stress. It also reduces shear stress toward the end, toward the edges, but overall keeps them protect the adhesive bondage. You can kind of see how you can change the design to minimize the impact on the bond. You can see this, and when you connect the stringers, for example, to the wing skin or to the fuselage, if you look at the end section, you can see this tapering. Do you see this tapering? That's the exact reason you taper toward the end. So this is a T-blade, or this is a blade stringer that you bonded to the surface. It's only good under shear. When you get close to the edges, you will develop peel stresses. To prevent development of peel stresses and create delamination, you taper them. But sometimes it's not enough, and you might get the condition that start developing peel stresses. That's why you might add fasteners toward the end, or you might have other like more complex design. We're going to talk a bit about that. You might have some more complex design approaches toward the end of parts like that. Questions? Okay, so I hope you can start to see some of the challenges of having a bonded joints on an aircraft, and what are the things that you have to pay attention to. Temperature affects the adhesive properties. This shows the shear stress strain curve. If you take an adhesive and do like a lab test or shear lab test, where you put it's typically the test that you might do is similar to this, perhaps, and you maybe hold one of the substrates and you pull the other one, so the adhesive goes into shear, and you can measure the properties of adhesive. It could be through that process, or you might do a pure shear test. But either way, if you do the test at different temperatures, you can see a wide range of properties that are on display for this adhesive. If you are going to the cold temperatures, it becomes more brittle. It's not a ductile response. Around room condition, typically most polymers under shear, they behave in a ductile manner. So they have plasticity. Unlike under tension, that they're brittle. Under shear is something along the polymer chains aligning themselves, and it allows for some plasticity. And as you go to higher temperature, it becomes more and more and more. And if you go beyond the glass transition of the adhesive, it just falls apart, right? So your adhesive goes through this wide range of properties, and you have to design your bonds for any given temperature and humidity conditions. You can kind of see now the difficulties of having only adhesives. You have to consider its brittle condition and its ductile condition, depending on the temperature. Other things that affect adhesive: surface preparation. So again, in the single lap shear test, let's say you are taking the two surfaces, you're preparing the two surfaces using different methods. And this is one study that the FAA has done, where they take the samples out of manufacturing, untreated, they put adhesive between them, and do a single lap shear test. They measure the strengths. You might have something we call peel fly if you're familiar with that process. But during manufacturing, there's a sacrificial consumable on the surface that can peel after the manufacturing. It's quite common practice, at least when you're making like tensile coupons like that, to do this, because then the surface becomes rough and ready for tabbing that you need to do for tensile testing. So sometimes it's a common practice. But this material itself can be polyester based. You can see it reduces the strength. It can be nylon based, and it shows a wide range of properties depending on if you repeat the test. If you don't have it, just use sandpaper to roughen the surface and then use alcohol to clean the residue. The strength goes up significantly. That's probably the best way of preparing the surfaces. It's common practice that you take the as manufactured material, you use a sandpaper, slightly roughen the surface, not breaking the fibers, and then you clean it with IPA, with alcohol, let it dry a bit, and then you do the bonding. Sometimes you use plasma treatment to prepare the surface even further. Any other
question?
Yes.
Is there a concern about dust being left after you sand it that will be left behind by the IPA?
Yeah, it's a good point. So for manufacturing, you're not going to do sanding probably. I don't think they're going to do sanding if you're in a manufacturing environment because of what you mentioned. But for testing in the lab for coupons small size, it's a common practice. So we were doing it this way: sanding it, then use air pressure to clean it, and then use alcohol to further clean it.
Thank you.
Okay. So from all I mentioned so far, it seems that in some cases, there is no other option but to use fasteners. Even though it's expensive, even though drilling is expensive, putting the fasteners are expensive, fasteners themselves are expensive, it's heavy, it reduces the, it increases, sorry, it adds a lot to assembly time if you wanted to go through that process. But sometimes to have a safe structure, it's quite necessary to have fasteners. So a couple of considerations for fasteners. First of all, they fail through different failure modes as well. I'm not going to go into details of that, but it might have quite different failure modes where in some cases you might break the material, or there is a definite bearing effects from the fasteners on the part, or you might break the fasteners or bolt themselves. Most of this you can mitigate through proper design. So for example, if the load is too much on a fastener, you start adding to the number of fasteners. Kind of distribute them such that the load is carried by more than one fasteners. One fascinating thing that I was not fully aware of is the effect of fasteners on lighting strike protection. If, let's say you put the fasteners and there is a bit of gap between the fastener and the composites. When the lighting strike happens, the energy comes in and there's gap, and that gap creates sparks, and that spark might lead to fire. So there is a very tight tolerance on all the gaps that you might have when you're doing this type of bonding or joining. So there's lots of details in terms of what you have to consider when you are doing the design. I mentioned you can eliminate many of the failure modes I mentioned in the previous slide. There are recommendations by FAA. For example, remember the triangle for the percentage of the layers? It's recommended that don't explore very weird types of stacking sequences where like most of the layers in one direction and then there's just a few on the other direction. So the recommended area to keep the balance between different layers, and we have figured out that these recommended areas can keep the material from failing around fasteners. So there's recommended, and then beyond that, you try to avoid. There is joint configuration effect. Here is one example. Remember, I mentioned you can bring the couple of different materials in different ways. Here shows you you're bringing two layers from one side and one layer from the other side. And in one case, you taper them and then put 4 bolts in it. In the other case, you don't taper them. And in the other one, you taper 2 of them. This graph here shows bolt number versus the load on each bolt. And you can see that based on the way you are bringing this component together, the stress on the bolts goes up and down. The best design is this triangle, which is the configuration 1, which you taper all parts, then you bring them together. The worst design is this, I think 4 and 3, there's different sizes of bolts, but if you compare 2 and 3, 2 is the circle one. So it gets really high stress at the edges. It's not a good design at all. Okay. Any question by the way so far? Let me mention one more topic about fasteners, and I'm gonna close the class today with one slide, which would be the focus of your final discussion topic. There is this consideration for composites. In general, when you're designing with fasteners, the terminology that you have to know is the bypass force, how much force is going through the area with fasteners, and then how much of that gets transferred to the material around the fasteners, the bearing load. So the bypass bearing load. In metals, it's important considerations because it brings fatigue into the picture. So they consider this trade-off between how much loads goes and then how much of that goes around the bolts to kind of look at the fatigue problem. In composite, though, it brings in other problems, and that is depending on the load that comes in, you might get different failure modes, and that makes it challenging. For example, under tension or compression, the type of stress distribution around composite changes, and the points that go into tension and compression varies, and you might get tensile failure versus compressive failure, or different location for tensile or compressive failure for composites, which has to be part of the design. Depending on the, let's say, the size of the specimen versus the size of how much of this is cut out, you might get different micro level failure modes, which changes the failure stress at the end. So there are some extra consideration, which I'm not going to go into details because it gets too technical. Just for you to be aware of, there is a difference between metal and composite when we're talking about fasteners. And the main problem is that composite have a lot more failure modes around fasteners. And 2, the lightning strike becomes an issue. Lightning strike protection becomes an issue around fasteners. Okay, let me close the lecture today with this slide, which is the basis of your one of your discussions. In general, you might get to a situation when even bolts and fasteners are not enough to protect the material. There are cases that first of all, it could be cases that the design is quite sensitive, or there's quite a number of fasteners coming into one play, or the design was such that you could not properly protect the material, or you just want to have like additional safety factors. In these cases, you don't rely on fasteners alone. You put in metals around fasteners, like this example here that shows the corner of an opening where there's too much stress concentration, and the flow of stress is such that some of these fasteners might start imposing high-level loads to the composite around them and start a failure mode. So you're going to protect that area further by putting like a metallic plate. Sometimes you go one level further. For example, this shows a vertical stabilizer and a horizontal stabilizer. In this case, you want to connect the vertical stabilizer, for example, to the horizontal stabilizer. And instead of connecting them directly, because of all the loads that you have in this case, You might transition from composite to titanium, do the bonding to do the joining, and then transition back to composite. So that's a common fitting, is a terminal fitting of the vertical stabilizer to fuselage. So different cases. In sometimes when you have stringers, you might choose to put the metallic plates right at the ends, in addition to bolts that you're putting at the end, to further protect the material. Okay, good. So any questions on the lecture, the discussion topics, or your midterm next week? Again, midterm would be on Canvas next week. You have to log into Canvas at 11:30. A quiz becomes available. You have 1 hour, 20 minutes to take the quiz. And it's a closed book, closed notes quiz. Pay attention to slides, pay attention to the recordings of the class, go over the discussions that you have had with Christos, and you will be fine for sure. So there will be no surprise in the exam. Any additional questions? Are we good? Great. Thank you, everyone. Sorry that I had to do the class today on Zoom, but I think it's for everyone's benefit. I'll see you virtually on Zoom next week. Thank you.
Thank you.
Thank you. Thank you, everyone.